What's up, kidlets? Today we're going to be looking at stationary points. Now, your textbook does two chapters, 10C and 10D, on stationary points, but it's all pretty much the same thing. It makes a lot more sense just to roll both exercises into one. So that's what we're going to do. Alright, so a stationary point occurs when the gradient of your function is equal to 0. So it's solved by finding where your derivative function equals to 0. And there are two types of stationary points that you'll come across. You can get a local maximum or a minimum, which is what we refer to as turning points, or you can get a point of inflection. Now, our maximum and minimum turning points are referred to as local maximums and minimums because they're not necessarily going to be where the function is at its absolute maximum or absolute minimum. So it's just local to that particular area. Alright, so in this little diagram here, at A, we have a local maximum, and C is our local minimum. Can you guys hear Monty meowing in the background? I think he'd be happy, he's just been fed. And that leaves B to be our point of inflection. Alright, so stationary points are important to be able to identify when sketching functions. It helps us to accurately plot our graphs of our functions. And later on we're also going to solve problems using stationary points to find where functions maximize or minimize. But to begin with, we're going to work on finding these stationary points and then justifying or stating their nature. So by that we mean whether it's a local max or minimum or a point of inflection. So our first example here. Find the stationary points in the following and state their nature. So our first step is to always find where the derivative is equal to 0. So we're going to derive this function first. So that's going to give me 12 minus 4x. We then want to solve for where that function is equal to 0 to identify the x coordinate where the stationary point occurs. So this is going to be x is equal to 3. So we know at x is 3, I'm going to have a stationary point of some nature. And by substituting that value back into our original function, we can find the corresponding y-coordinate as well. So that's 27. Alright, so my stationary point is occurring at 327. Now, you might be saying to me, well, miss, I've got a negative quadratic up here, so obviously this function has to have a local maximum. And you would be right, but what if your question then asks you to justify or prove that it's a local maximum? Well, the way that we do that, there's actually two ways we're going to look at to do this. The first way we're going to look at is called a gradient table. So the gradient table tells us what the gradient is doing either side of our x-coordinate. So for this, you want to select points either side of your x-coordinate and check what the gradient is doing either side of that point. So you can pick any point smaller and any point greater than our x-coordinate. So 0 is a pretty easy number to use, and then we'll just use 4 as well. Now we know the gradient when x is 3 is 0. So now what I want to do is I want to check what the gradient's doing at x equals 0. So I'm going to take 0 and stick it into my derivative function. So I'm going to have 12 take 4 lots of 0, which is going to be 12. So that's a positive value. I don't actually care what the value it is itself. I just want to know whether it's positive or negative. So when I chuck 4 into my derivative function, I get 12 take 16, which is going to be a negative value. So that means the shape of this function goes positive gradient, 0 gradient, negative gradient. And that means that I have a local maximum. And there's a couple of other shapes that you'll get. So this is our local max. We can also get, that would be a local minimum. and then we can get a point of inflection or another point of inflection. So that they're all the different ways, all the different shapes that our gradient table could take. So it's a positive point of inflection and a negative point of inflection. Cool. Alright, so that one was pretty straightforward. Derive the function, solve for it's equal to 0, state the nature of the stationary point by substituting into our gradient table. Let's look at something that's slightly more challenging. Now we have a cubic function. So for our cubic, we're expecting there to be 2 stationary points, unless it's in a point of inflection form, which this one does not appear to be so. One of those is going to be a local maximum, one of those is going to be a local minimum. We're going to follow our same steps. First thing I'm going to do is derive the function. So I get 6x squared, take 10x minus 4, and then I'm going to solve where that is equal to 0. And for your purposes today, I'm not going to factorize and solve this by hand because that will take too long. So I'm just chucking it in my calculator and solving for x to save us all the problems of me doing it on the calculator while you guys watch. So I get x is equal to negative 1/3 and x is equal to 2. Now if I chuck these into my calculator to get the corresponding y values, the coordinates are negative 1/3 and 370 on 27 and 2, 1. Hooray! Alright, so they're going to be my 2 stationary points. What I need to now determine is which one's which. Which one's the maximum, which one's the minimum. You might be thinking, well, that's pretty obvious, miss. The 370 on 27 is a bigger value than 1, so obviously the first one's going to be the local maximum and the second one's going to be the local minimum. Duh. But again, you might be asked to justify the nature. This time, rather than using our gradient table though, let's have a look at another method that we can use, which is technically in the specialist math course. But you're encouraged to use specialist math knowledge in methods if you have it, and I find this method quite straightforward as well, so we're going to go with that. And it involves using our double derivative or second derivative. So the notation for this is d squared y on dx squared is our double derivative, and it means just taking our first derivative and deriving it a second time. So that's going to be 12x take 10. Now, if your double derivative is greater than 0 when you substitute your x value in, if it's greater than 0, then that means that you have a local minimum. If it is less than 0, that means you're going to have a local maximum. And if it is equal to 0, you guessed it, that gives us our point of inflection. Alright, so for each of these now we can just take our x values, so negative 1/3 and 2, chuck it into our double derivative or our second derivative, and depending on whether our value is positive, negative or equal to 0, we can then determine the nature of that stationary point. So let's check x is negative 1/3 first. So, got cat hair on my computer. 12 lots of negative 1/3 minus 10. Again, I don't really care what this equals. I just need to know whether it's positive or negative. So 12 times by negative 1/3 is going to be negative 12 on 3 is negative 4. Take 10 is going to be a negative number. Alright, so because it's less than 0, this must mean that it's a local maximum. So negative 1/3, 370 on 27 will be a local maximum. Let's now check x is 2. We get 12 lots of 2 minus 10 and that's going to be a positive value. So because it's greater than 0, that's going to give us a local minimum. So it's the opposite of what you think it'd be. You think if it's a positive value, then it's going to be a local maximum, but it's not. It's the other way around. So 2, 1 will be our local minimum. Cool. Now some alternative notation for your double derivative. If you're given it in terms of function notation, that's f dash dash. 2 dashes for your second derivative. Makes sense, doesn't it? Alright, moving on. Alright, this is a very common kind of question that is often overlooked in both SACs and exams. It's where we're finding the values of unknowns, and we know that depending on the number of unknowns that I have, that needs to equate to the number of equations that I'm going to set up, which should equate to the number or the bits of information that I have. So 3 unknowns should mean 3 equations, which should mean 3 bits of unknown. Alright, well, straight off the bat here, we can say that C is equal to 5 because, well, 0, 5 is the y-intercept. So that still leaves me with A and B to solve. So I've still got 2 unknowns here. And looking at this question to begin with, we're going, oh, well, I've only got 1 other coordinate. But we're also told that I have a stationary point at this particular coordinate, which means that I've got information about what the gradient is doing at that point. So if I have my derivative function, I can take that information, substitute it into my gradient function, and then set up a second equation. So let's start with the point 27, and we're going to put that into our original equation. So I get 7 is equal to 2 cubed is 8 plus 4a plus 2b plus 5. And if we transpose all this crap over, we get 7 take away 8 is -1 minus 5 is going to be -6 equals 4a plus 2b. And we can simplify that down, so we get -3 is equal to 2a plus b. So there's my first equation. Sweet. Alright, so now I haven't got any other information that I can substitute into my original function. But I do have information about my gradient. I know that because I have a stationary point, my gradient is going to be 0 at x equals 2. So I'm going to substitute this into my derivative function, which is, what's my function? That's going to be 3x squared plus 2ax plus b. Alright, so I know that 0 is going to equal 2 squared is 4 by 3 is 12 plus 2 by 2 is 4a plus b. So -12 will equal 4a plus b. And that gives me my second equation. Hurrah! And now I can just solve these things simultaneously. And you can either do that by hand or using your calculator, depending on whether or not it's exam 1 or exam 2. So let's assume this is exam 1, because who doesn't love doing all the math? Let's do -12 equals 4a plus b minus -3 equals 2a plus b. So -12 plus 3 is going to be -9 equals 2a, and b's will cancel out. Just be careful with your notation here as well. Make sure your a's don't look like 9s and vice versa. This is one of those things that examiners are all like, make sure they look different, because otherwise, you know, you misread your own writing and then you fuck it all up. Alright, solving for a here gives us -9 on 2. Sweet. Alright, let's chuck that into our first equation now to solve for b. 2 lots of -9 on 2 plus b. It's a terrible b. Alright, so -3 will equal -9 plus b. So 6 will equal b. There's another one. 6's and b's, they look the same as well. So make sure they don't look the same. Alright, and then finally we should state our values for a, b, and c. So a is -9 on 2, b is 6, and c is 5. Cool. And that is stationary points.